Alright, so today I'm gonna be explaining this important paper with the title Finding Global Homophily in Graph Neural Networks When Meeting Heterophily. This ICML paper in 2022. We investigate graph neural networks and graphs with heterophily. Some existing methods amplify a node's neighborhood with multi-hop neighbors to include more nodes with homophily. However, it is a significant challenge to set personalized neighborhood sizes for different nodes. For other homophilous nodes excluded in the neighborhood, they are ignored for information aggregation. To address these problems, we propose two models, which generate a node's embedding by aggregating information from global nodes in the graph. Based on implicit graph homophily assumption, traditional GNNs adopt a nonlinear form of smoothing operation and generate node embeddings by aggregating information from a node's neighbors. So homophily is a key characteristic in a wide range of real-world graphs where linked nodes tend to share similar features or have the same label. These graphs include friendship networks, political networks, citation networks. However, there also exist graphs with heterophily, where nodes with dissimilar features or different labels are more labeled. So in the past 7 or 6 videos, I was talking about this heterophily. So you are already familiar with this. But a research question arises, can we find a global homophily for a node and develop a GNN model that is both effective and efficient for heterophilous graphs? So we first show how to capture node correlations and derive the coefficient matrix Z in each layer. After that, we introduce how to accelerate the neighborhood aggregation based on this correlation coefficient Z. Connected nodes are more likely to have different labels in heterophily graphs, while distant nodes could be from the same class. We have to enlarge a node's neighborhood to leverage more distant nodes. A straightforward way is to use all nodes in the graph. We characterize each node by all the nodes in the graph. So in the else layer, we can determine the coefficient matrix Z. And now here, O is the noise matrix. We can interpret Z as a value that reflects how well node X sub J characterizes X sub I. So Z plays the role of a weight matrix. Since it has been pointed out in this reference that oversmoothing problem is caused by coupling of neighborhood aggregation and feature transformation, we decouple these two processes. But first, performing our generated MLP, we use MLPs to map feature matrix and adjacency. Then we derive the node embedding. After getting the MLPs, we have the representations of both feature matrix and adjacency matrix. Now we have a node embedding matrix. So this gamma is a hyperparameter that balances the term importance. We characterize node correlations based on edge. If two nodes share similar local graph structure, they are more likely to have the same label. We measure node correlations in terms of both feature similarity and topology similarity by further regularizing with nodes multi-hop reachabilities. So we have this objective, minimizing this objective. To show the importance of the kth hop graph connectivity, we further introduce a learnable parameter lambda. The objective has three terms. The first term reduces noise and drives the linear representation for nodes to be close to their own embeddings. And the second term is a Frobenius norm, and the third term regularizes by the multi-hop regularized graph adjacency matrices. So this is the closed form solution to optimization. And we can write neighborhood aggregation in the else layer. So directly updating H using this equation is infeasible due to cubic time complexity in computing Z and the quadratic time complexity in calculating this term. So to accelerate the updates, instead of directly calculating Z, we transform 6 into this one. Now Q is here. I is the identity matrix and C is the number of labels. So we avoid computing Z directly and can accelerate the updates of H by matrix multiplication reordering. So we first compute Q, where the second term is calculated from right to left. The matrix inversion is performed on matrix in R C by C. For a node V sub I, we denote A as the ith row, and so we have this grouping effect. A matrix C is said to have grouping effect if this holds. And then they show the grouping effect, this property in this lemma. So this grouping effect explains the effectiveness of their model. In fact, for any two nodes, no matter how distant they are in a graph, if they share similar feature vectors and local structures, so they will be similar coefficient, they will play similar roles in characterizing other nodes, and they will be given similar representation vectors. Now, the coefficient matrix Z plays the role of longitudinal attention that characterizes importance of a node to another. In neighborhood aggregation, not only varies the importance of nodes' neighbors, but also that of hidden features. For example, in node classification, the imbalance of node labels could lead to various importance of hidden features corresponding to different labels. So we further upgrade our model by considering horizontal attention with respect to hidden features. We introduce a diagonal matrix such that sigma describe the importance of the ith dimension in H. So we have this optimization problem in this paper. We are minimizing over Z. And of course, we can also accelerate neighborhood aggregation. And we next discuss the major differences between our models and the adapted GATT model that takes global nodes as neighbors. First, the attention weights are automatically learned in lack of interpretability, but the Z in our model is derived from a well-designed optimization problem and has a closed form solution. Second, the attention weights are always non-negative values. Therefore, GATT only employs low-pass convolutional filters, while our methods combine both low-pass and high-pass filters. So these are the data sets that they compare different models like MLP graph convolution, graph attention, to their models GLOW, GNN+. Also, the classification over other 6 large-scale datasets.